Taylor-Maclaurin series. Let's build from scratch. That's going to be the first example. And then we're going to use the known one. To build from scratch, you need to know the formula, which is the original function at the center a, which can be anything else, not just 0. Divided by 0 factorial, x minus a to the 0, plus f at 1, but first derivative, not at 1, at a. First derivative divided by 1 factorial x minus a to the 1. That's the pattern. 0, 0, 0, 1, 1, 1. And it's going to be 2, 2, 2, which is second derivative. 2 factorial x minus a squared. And it's keep going. This is the formula we're not going to give you in a test. You have to know it. It's very important. In general, if you show it around the world, people know this is Taylor formula at any kind of center. No derivative, first derivative, second derivative, third derivative, and so on. The coefficients are these numbers attached to the unknown, which is x minus a. These are CNs in yellow. That's what sometimes we ask you to find these or build the whole Taylor from scratch. So, example, let's do the example. Example 1. If I give you a function f of x, that's what we give you in a test. F of x is 1 plus x to the minus 2 at x equals 1. Two ways to find the series. So build or find Taylor series at x equals 1. This is even better. Either you use the known series, but the known series, which are Maclaurin series, only work for a0. That's what they call Maclaurin series. They're Taylor series at 0. And sometimes even they don't help. Then you have to build it from scratch. You're gonna do it this way. So I have a student I mentioned to you before who always writes down the formula right away. And I like it a lot because this makes you a habit. This is the function. This function has an infinite Taylor series, which is the original, so it's f of, this is 1 plus x to the minus 2, at 1 plus, so divided by 0 factorial and blah, 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 that's 1. The first derivative at 1 divided by 1 multiplied by x minus 1 to the 1 plus second derivative at 1 and an x minus 1 squared divided by 2 factorial plus and so on. Our job is to find these coefficients. And now how you find it, that's your way. How do you sort or organize information? I like using tables because it looks organized. Yeah.
How's the Taylor series against x minus 1?
So Taylor series is a general case. Taylor series has minus center, minus center, minus center. And we told you, find Taylor series, and I can ask at 0, I can ask at 17. This time I ask at 1 just because it's easier to calculate. Did it answer your question? So it's minus center, x equals 1 is new center. Make sense? Was that your question?
Yeah.
Okay, thank you. Yes?
So why is it f of 1? Because it's x and you have f of a is, that's why I'm confused.
Yeah, I can see. A is 1.
Oh, so a equals x.
Yeah, I have to say A is not international notation. Sometimes they call it C, A, x sub 0. So when we call it center, or we'll say find Taylor series expansion at 1, that means the center. This phrase at 1 is the center.
So f of the center.
Yeah. So center is A. Plug it in the formula everywhere where you see A.
And then x plus or minus the displacement.
Yes.
Center. Okay.
Minus center. Exactly. Thank you. Good questions, people. Now, I like to create a table, but you don't have to. The first thing you do is you write down the original function, and then you right away can find this original function at the center. So it's going to be 1 plus 1, which is 2. 2 to the minus 2. Does it make sense? So I do it right away. If you speed up, that's going to help you on the test as well. So original function is 1 plus x to the minus 2. Plug in. Why did we plug in? Because now we have this coefficient in yellow, except we did not divide by the corresponding factorial. But the first one is just divided by 0 factorial. Now, this is the coefficient called c sub 0. This is called c sub 0. Moreover, we know that c sub 0 will be multiplied by x minus 1 to the 0. Does it make sense? So I have 3 columns usually. The fourth column is just to remind me that it's going to be multiplied by the corresponding x minus a to the power. And that power is 0 step, so it's going to be 0. That's step 0. Step 1 is now derivative. Minus 2, 1 plus x to the minus 3. I really hope you're not going to mess up derivatives on the test. It's like very upsetting to see everything is fantastic except the derivative. And I did not put chain rule there. Like no, this one has chain rule, you know, it's actually times the derivative of the function inside. And I did not even do that. It's just like, try your best. Don't integrate instead of differentiation. Those things also happen. I know people panic and just like the brain gives weird information. I totally understand. The first derivative at 1 becomes minus 2 times 2 to the minus 3. That will be divided, so minus 2 times 2 to the minus 3 will be divided by 1 factorial. To be honest, I just remember that the first 2 do not change, so I don't care. This one is multiplied by x minus 1 to the 1. Second derivative is minus 2 times minus 3, 6, 1 plus x to the minus 4. When you plug 1, it will be 6 times 2 to the minus 4, and now you see the pattern. 6 times 2 to the minus 4 divided by 2 factorial. That is c sub 2 and will be multiplied by x minus 1 squared. And let's keep going. Coefficients are in the third column. Those are coefficients, Coefficients are in the third column. But just remember, if you don't remember the formula, if you forgot the formula of Taylor, which is over here in the box, yellow are coefficients. This is why the last column is actually pretty clever to have. You multiply this plus you multiply this. So you multiply third and the fourth column and add those things together. And that gives you Taylor polynomial, Taylor series. Let's write it down. It's going to be answer 1 plus x to the minus 2 equals infinite polynomial. The first coefficient is 2 to the minus 2 multiplied by x minus 1 to the 0. I just keep it. The second one is minus 2 times 2 to the minus 3. I don't even simplify. I will not ask you to simplify. It's fine. Multiplied by x minus 1 to the 1 divided by 1 factorial. Plus 6 times 2 to the minus 4 over 2 factorial. X minus 1 squared. Who wants to give me the one more? Because the pattern now is pretty clear. Do you see the pattern? 2 to the minus 2, 2 to the minus 3, 2 to the minus 4. It's also changing the sign. What do you think? Negative 24 times what? 2 to the minus 5. 3 factorial times. Amazing. Amazing. Thank you. See? Look at that. So now you see the pattern. And that's why usually we don't simplify. That's why I did not bother to divide by 6. 24 over 6 or 6 over 2. Because pattern then it's more obvious in this way. This is the answer. Can you do this problem? Usually, not always, but usually on a test we put it in the free response. If this is all the free response problem, this costs like 12-14% of your exam. Can you do this? See? You can. So it's amazing. Amazing. And it's also on the quiz right now, so it's good. So that's what I wanted to practice. Questions? I'll give you those notes, don't worry. Now, one more thing. Example 2. what if we can use the known one, the known series? So for example, x to the 4 over 4 minus x squared dx. X is less than 4. They ask us to integrate this function. This is one of the applications of Taylor series. To be honest, Wolfram Alpha uses Taylor series. Every time you ask integrate some ridiculous function, it does not give up. It either uses numerical approximation, Simpson's rule or whatever, or it uses Taylor series. It really quickly does this formula, and it knows this formula. Wolfram Alpha and Geographing Calculator, they both know the Taylor series. Really quickly, they create this, and instead they integrating this or differentiating, and gives you like 17 digits after the decimals after the, right? And then it just stops. It aborts integrating when the memory runs out. So it tells you, oh, it's too long to integrate, this is what we got. That's how it approximates some ridiculous integrals. That's why it's so important. It's only one of the applications. Okay, so you try to integrate this using U substitution, maybe then integration by parts, maybe like plug in secant, hope for the best. Did not work. Then you do numerical integration, but before numerical, it's very popular to use Taylor series. So we're gonna create series for this function inside. Step 1, solution. So solution. Step 1, build series for the function inside for f of x. Let's call it f of x. X to the 4 over 4 minus x squared. Let's build this series. And again, you have two ways to do it. From scratch, that's what we just did, building a whole table, or using the known ones. But it looks like geometric series. And that's why we're like, I don't want to build it from scratch because it will be quotient rule. The answer will be the same. For you to know, table integrals are created from scratch, okay? So, except geometric series is created from geometric series formula. Everything else is built from scratch. That's why they're called basic, because someone did it for you. Now, let's use those basic McLaurin series to build new functions, to build series for new functions. So, let's choose not to do it from scratch, but you can check, actually, it will give you the same answer. Using known McLaurin series. And we got, what is that? And we're gonna use series. We're gonna use geometric series. Geometric series. Don't worry, I'll put all those formulas on the test for you. So you don't have to memorize any of this. But remember, 1 over 1 minus input has a series input to the n from 0 to infinity. This only works when x is less than 1 by absolute value. Geometric series. So this is the one you don't have to memorize, but usually it's so popular, everyone knows it. Geometric series. I will even on a test will tell you which series to use. So there's a table, but to be honest, you don't need it. It's only distracting more. I will tell you, use this for that, and then for sine, use this for that. So that's what I did. On a test, I already put everything there. Not all instructions like it though. But I think it's better. It saves lots of time and frustration. So what we're gonna do is we're gonna write down x to the 4 over 4 minus x squared, and we'll try to create series from this. I will kick out x to the 4 and we'll work with 1 over 4 minus x squared, because this does look like geometric series. I will speed up a little bit and you tell me if you have questions. I like 1 over part, and minus x squared is fine. I don't like 4. So we'll factor out 4, and I'll have 1 minus x squared over 4, like so. Now, I can see, maybe you can see too, that x to the 4 over 4 are multiplied by a nice function that is ready to have series created using geometric series. The one in green. The one in parentheses. This is exactly matches the idea of 1 over 1 minus input equals sum input to the n equals x to the 4 over 4, or keep waiting. And now you have a sum. Input x squared over 4 is new input to the n. New input to the n. From 0 to infinity. Sometimes people skip writing n equals from 0 to infinity, but you will see it in upper level classes. People skip it. Now, submerge, that's not correct to say, I just like it. Submerge x to the 4 over 4 into the sum, which is distributing. It's a sum. So let's just multiply by this term. We are almost done. It's a sum, x to the 4 over 4 times x squared over 4 to the n, from 0 to infinity. This is a good answer, but it's not enough. It's not enough. Just let me finish for a second. Because if you check practice exam, I give you sums there to choose from, and they are simplified. That's the criteria of the school. They are simplified. So how would you choose if you don't simplify? See? I will tell you which series to use. You use them, and now they're all messed up like so. And you need to know which one to choose. Thus, you need to collect terms. It will be sum x to the 4 times x to the 2 plus n, or 2 times n. Which one? 2n. That's the properties of exponents. I'll review it in a second too. All over 4 times 4 to the 2n as well. No, 2n, just n. N. So what I did, I put n on both sides of the fraction. Finally, the answer follows. The answer is x to the what? Who can tell me? 2n plus 4. Let's write 4 plus 2n, but I like 2n plus 4 more actually, but just to have good notes. 4, 1 plus n. This is the answer. If you have 4 or 5 sums in the multiple choice question, you choose this one. And I will just review for you what just happened, called properties of exponents. If you have x to the a times x to the b, you add a and b. But if you have x raised to the a, then raised to the b, maybe even raised to the c, the more you raise, the more you multiply. Like so. This is a review of the properties of exponents from pre-calculus class, I think. How about that? What do you feel about that? Very good. This is how you work with series. Is this the answer? What was the question? Let's see. The question was to find the integral. That's the catch. To find the integral. If on the test you see that, don't mess up. On the quiz, I did put that. If they ask you to integrate, that's the whole point, was we could not integrate that thing. Now we have a new thing, a series. So we had step 1. Step 1, build a series. Check mark. Step 2, now you do whatever you want to do with it. Maximize, minimize, concave up, concave down. If you want to differentiate, differentiate. Want to differentiate 5 times? It's easier to differentiate this than some crazy function. Integrating, same thing. You can integrate double, triple integrals of this is easier. Integrate. Integrate. Integrate is integral of this sum. Many of you write down the terms, which is not wrong, but it's actually easier to integrate the sum. I will try to explain you right now and prove to you that it is easier. It looks worse, but it's not. This is what we're doing here. See, show your parents this. This is pretty awesome. Like this slide is really good. Look at this integral and sum, and they will like, wow, our kid's working so hard. We should buy them a car. That would be nice. And then you come here and tell me thank you. So, we're gonna integrate not term by terms, but right away. Check out, very interesting actually. So dx is important because it tells you what is the variable for the integral. X is the only variable. 4 to the 1 plus n is a constant. We do not touch it. Thus, it becomes even easier. It's not quotient rule. It's not integration by parts. We only have power rule, x to the 4 plus 2n. So I will have 1 over 4 to the 1 plus n. N plus 1 is better, to be honest, but it's fine. Just keep it. This is a constant. This is a constant. We don't touch it. But it's multiplied by x. X to the 4 plus 2n. Integral of that is what? 4 plus 2n and what?
Times 2.
No. Good guess though. Plus 1. We're integrating, remember? We're integrating, not differentiating. Over 4 plus 2n plus 1. Power rule. Integral of x to the n dx is x to the n plus 1 over n plus 1. Something is missing? Plus c, thank you. Plus c. Let's simplify. And we have the answer. So because bc, or used the formula called power rule. Finally, the answer follows. The answer says 1 over 4. Let's write nicely. N plus 1 times x to the 2n plus 5 over 2n plus 5. N is from 0 to infinity plus c. This is the answer. Some of you will argue, why not to do it term by term though? Let's try. Why not? We can do it term by term too. And I'll show you how to do it in a second. The thing is, the answer will be the same. The answer will be the same. Let's check it out. Well, let me slow down and ask if you have questions. So plus c is outside. It's not inside of the sum. Do you know that? The sum is infinite sum. Sum. And at the very end, there's a huge fat plus c. It collected all the constants together and stuff. So you see, we integrated the whole sum. Adding 1 divided by the new power, like so. Power rule. Not too bad. Then you can ask me, what if I don't like this notation of integral and sum? Well, you should try to get used to it. But fine, some of you like to work with terms. So, or integrate term by term. You came right on time for the joke I want to make. I will make some inappropriate joke today. Or integrate term by term. Integrating term by term is, okay, let's write down the original sum again. X to the 4 plus 2n over 4, 1 plus n. Before we integrate it. This is what we have here. If I write down terms of this sum, I can integrate term by term too. So let's practice that. N is 0, n is 1, n is 2. And then we're going to integrate those one by one. And those are polynomials, very simple. X, so when n is 0, it will be x to the 4 over 4. Agree? Right? When n is 1, it will be x to the what? 6 over 4 squared. When, that's too far. When n is 2, it's going to be x to the 2 times 2 is 4, 4 plus 4 is 8 over 4 to the 3. Now you see the pattern. That is the pattern. X to the 4 to the 6 to the 8. 4 for square, for cube. Do we change signs? I don't think so. So now we can actually integrate that. Integrate term by term is, check it out what I'm going to do. I will put integral outside of this dx, just like we did before. Dx is extremely important now. You keep losing dx in your exams. I was keep writing it for you and I did not take points, I think, except the first exam. Because it's very important. If I put dn here, it will be much more complicated actually to integrate. And I can, it's legal. So dx is important, it tells me what is the variable. X is the variable. So we're integrating this now, term by term. Check it out. Infinite polynomials. Pretty cool that we're integrating something infinite. And the rule will be the same. 1/4 x to the 5 over 5 plus 1 over 4 squared x to the 7 over 7 plus 1 over 4 cubed x to the 9 over 9 plus, and keep going, plus fat c at the end. It should be the same answer. If you collapse it back, it should give you, so this answer should be the same as the one we got in the sigma notation, which is some notation. You can check if it's the same or not. Plug n equals 0, it better be 1 over 20 x to the 5, and so on. Plug n equals 1, and it should be also second term, and so on. Does that make sense? You can do both, but if you check the practice exam, I actually give away the style of the test. Most of them are using sums, something like this. I already showed you that. Using sums. So integrating, differentiating, most of them are written in terms of sums. You need to know how to deal with it. So we worked on this in my office hours today. Does it make sense? Do you think it's okay? Inappropriate joke helps people to remember how important dx is. I learned it in America. Very interesting. So the teacher goes to high school to teach math, to work, right? Goes to work. And keep walking, and passing by a kind of not very good neighborhood, lots of graffiti, inappropriate graffiti on the walls and so on. And then one graffiti just puzzles him. He sees this. Okay? And he's like, no, there's a kid so close to this place. How come? Don't teach people bad stuff. Don't forget, there should be dx at the end. Because it's integral e to the x dx. What did you think? Right, this is a good joke. It makes something good from something maybe also good. I don't know. It's kind of debatable. So integral e to the x. Well, it should be written like nicely. It's kind of like tilted. You see it like this. E to the x, integral of e to the x dx. And the teacher got so stressed. He's like, I keep teaching them and I keep forgetting to put dx at the end. He actually was sincerely thinking that dx is missing. Yes?
Did you say graffiti?
Graffiti.
Like, you mean graffiti?
Do you know how many years I'm telling this joke saying graffiti? Yes, it should be graffiti. I did not know that, actually. Thank you. I did not know that. We say graffiti. Graffiti. Well, actually, it sounds more beautiful. Graffiti. Okay, that was supposed to be graffiti. Thank you.